Welcome to this lesson on geometric progressions. A geometric progression, or GP for short, is a sequence where each term is found by multiplying the previous term by a fixed, non-zero number called the common ratio. Let's start with the basic formula of a geometric progression. If we denote the first term as a and the common ratio as r, then the geometric progression can be written as a times r squared, a times r cubed, and so on. Let's look at a few simple examples to understand this better. First, consider the geometric progression. 3, 6, 12, 24. Here, the first term is 3, and each term is multiplied by 2 to get the next term. So, the common ratio r is 2. Another example, 81, 27, 9, 3, 1. In this case, the first term a is 81, and each term is multiplied by 1/3 to get the next term. So, the common ratio r is 1/3. Now, let's derive the formula for the nth term of a geometric progression. If the first term is a and the common ratio is r, then the second term is a times r. The third term is a times r squared. The fourth term is a times r cubed. Following this pattern, we can see that the nth term, denoted as a sub n, is given by a sub n equals a times r raised to the power of n minus 1. Let's verify this with our first example. For the sequence 3, 6, 12, 24, where r is 3 and r is 2, the first term, a sub 1, equals 3 is equal to 3 times 2 caret 1 to 1, equals 3 times 2 to the power of 0 is equal to 3 times 1 equals 3. The second term, a sub 2, equals 6 is equal to 3 times 2 caret 2 to 1, equals 3 times 2 to the power of 1 is equal to 3 times 2 equals 6. The third term, a sub 3, equals 12 equals 3 times 2 caret 3 to 1 equals 3 times 2 squared is equal to 3 times 4 equals 12. This confirms our formula. Now, let's look at how to find the sum of the first n terms of a geometric progression. Let's denote this sum as s sub n. So, s sub n equals a plus a times r squared, and so on up to a times r raised to n minus 1. To derive the formula, we'll use a clever algebraic trick. First, we multiply both sides by r. r times s sub n equals a times r squared plus a times r cubed, and so on up to a times r raised to n. Now, let's subtract the second equation from the first. S sub n minus r times s sub n equals a minus a times r raised to n, factoring out s sub n from the left side. S sub n times 1 minus r equals a times 1 minus r raised to n. Finally, dividing both sides by 1 minus r, we get s sub n equals a times 1 minus r raised to n divided by 1 minus r, provided r is not equal to 1. For the case where r equals 1, the sum is simply n times a, since all terms are equal to a. If r equals 1, then s sub n equals n times a. Let's visualize a geometric progression to understand it better. Consider the geometric progression 1, 2, 4, 8, 16, where it is 1 and r is 2. Each bar represents a term in our geometric progression. Notice how each term is twice the previous term, which is our common ratio of 2. This visualization helps us see the exponential growth that occurs in geometric progressions with common ratios greater than 1. If the common ratio is less than 1, the terms decrease, leading to a decay pattern, like in our earlier example with r equals 1/3. Geometric progressions have many real-world applications. Let's explore a few examples. One common application is compound interest in finance. If you invest $P at an annual interest rate of r, compounded annually, then after n years, the amount a is given by a equals p times 1 plus r raised to the power of n. This is a geometric progression with first term p and common ratio 1 plus r. For example, if you invest $1,000 at 5% annual interest compounded annually, then after 10 years, you would have $1,000 times 1 plus 0.05 raised to the power of 10 equals $1,000 times 1.629 equals $1,629. Another application is population growth. If a population starts with p sub 0 individuals and grows by a factor of r each year, the population after n years is p sub n equals p sub 0 times r raised to the power of n. For instance, a bacterial colony that doubles every hour and starts with 100 bacteria would have 100 times 2 raised to the power of 10 equals 102,400 bacteria after 10 hours. Other applications include radioactive decay, spreading of diseases, and even the divisions in certain sports tournaments. Now, let's solve a practice problem together to reinforce our understanding. Problem. In a geometric progression, the third term is 18 and the sixth term is 486. Find the first term and the common ratio. Step 1. Let's use the formula for the nth term. A sub n equals a times are raised to the power of n minus 1. Step 2. Set up equations using the given information. For the third term, a sub 3 equals a times r squared equals 18. For the sixth term, a sub 6 equals a times r raised to the power of 5 equals 486. Step 3. Divide the second equation by the first to eliminate a. A times r raised to the power of 5 divided by a times r squared equals 486 divided by 18. Step 4. Simplify. R cubed equals 27. Therefore, r equals 3. Step 5. Now that we know r, we can find a. From a times r squared equals 18, and r equals 3, a times 9 equals 18. I equals 2. Therefore, the first term is 2, and the common ratio is 3. Let's verify. The geometric progression is 2, 6, 18, 54, 162, 486. The third term is 18, and the sixth term is 486, which matches our given information. Before we conclude, let's briefly discuss infinite geometric series. An infinite geometric series is the sum of all terms in an infinite geometric progression written as a plus a times r squared plus a times r cubed plus, and so on forever. Interestingly, if the absolute value of r is less than 1, the infinite series converges to a finite sum given by a divided by 1 minus r when the absolute value of r is less than 1. For example, the infinite series 1 plus 1/2 plus 1/4 plus 1/8 plus has it equals 1, and r equals 1/2. Since the absolute value of r equals 1/2, which is less than 1, the sum is 1 divided by 1 minus 1/2 equals 1 divided by 1/2 equals 2. However, if the absolute value of r is greater than or equal to 1, the infinite series diverges, meaning its sum is infinity or undefined. Let's summarize what we've learned about geometric progressions. A geometric progression is a sequence where each term is found by multiplying the previous term by a fixed number r. The nth term of a GP is given by a sub n equals a times r raised to the power of n minus 1. The sum of the first n terms is s sub n equals a times 1 minus r raised to n divided by 1 minus r for r not equal to 1. For infinite geometric series with the absolute value of r less than 1, the sum is a divided by 1 minus r. Thanks for watching. I hope you now have a solid understanding of geometric progressions and their applications.